4.2 is all about the electrons. Electrons on the move. We're talking about electrons on the move within the electron cloud and when they completely move out of the electron cloud or enter into a new electron cloud. So let's talk about these electrons. All right, the first part, we talked a little bit about color because we realized when electrons jump back and forth, sometimes they release some light in the form of visible light, and we can actually see that. This is why neon lights glow different colors. This is why the flame lit up when you put different chemicals in it. This is why your burner on your stove will glow bright red when it's hot, and so forth. So we need to know the different colors of the rainbow. So you should you should remember Roy G. Biv, red, orange, yellow, green, blue, violet. And you should also know which side has more energy and which side has less energy. So here's a long wavelength, meaning there's a big distance between the top of one wave and the top of the next. This is a long wavelength. Long wavelength is associated with low energy. Bigger distance, less energy. This is like if I'm standing at a toll booth and I'm collecting money. So here's my toll booth, and these are all cars. This car and this car and so forth. If they're going by and giving me money, I'm not going to collect a whole lot of money because there's such a big distance from one car to the next car. I have to wait a long time for the next car to show up to get money. So in chemistry, we don't talk about money, but we talk about energy. There's not a lot of energy in these waves. On this side, picture standing in a toll booth here, and you're collecting money from this car and this car and this car and this car and this car. That's a very short wavelength. Short wavelength. These cars are very close to one another in terms of waves. The waves are very close. If we were standing here trying to collect money and all these cars are going by because there's so many of them, I'm going to get lots of money. And in chemistry, we talk about high energy, lots of energy. Now, what do we know about colors? Well, when you did that little activity where you let light shine through, remember all those circles? And it went through onto tape, remember the fluorescent tape? The one that was red lit up the least. That wasn't bright at all. That had low energy. And the one that was violet lit up almost the most. The one that was just clear, had no filter on it, that lit up the most. But violet, that one of the colors that had the most energy, that was the brightest, that had the highest energy. So you should know your colors in order. If you know Roy G. Biv, you should now know that Roy, this side of the spectrum, has low energy. Doesn't do a lot for the electrons. This side, the Biv side, has high energy. Does a lot for electrons, makes them move a lot. So let's take a look at how this connects to the electrons. Now over here, we have electrons making jumps. We see this electron jumps out to there. This electron jumps way out to there. This one made a bigger jump. Now it was able to make a bigger jump because it took in more energy. When it jumps up and then it crashes back down, see the arrow going out and the arrow coming back in? It gives off a certain color of light. Now it takes in that light, that same color, to jump up, but then it gives it off. And when it gives it off, we can see it. That's what we can see with our naked eyes. So here comes the blue light out of the atom. We can see that. That would be part of an emission spectrum. It emits this light. Now this electron does the same thing. It absorbs red light. Over here, we see kind of a reddish-orange color. So it absorbs some energy, but it makes a small jump. It doesn't go out all the way to here like this electron does. It only jumps out to here. Now, because it took in a small amount of energy, so you see less energy, it's not going to go very far, and when it crashes back down, it gives off a color associated with low energy. So it lost one of these colors up here, the red, the orange, or the yellow, because that side's associated with low energy. So the size of the jump is determined by how much energy it gets, and then if it's a low energy jump, it's going to release red, orange, or yellow colors, and if it's a big energy jump, it gives off kind of a bluish purple color. And if you look over here at this picture, we see once more an absorption of a photon. Here's a little bit of light hitting this electron. The electron jumps up, and then as it zips around, eventually it jumps back down. And when it gives off, or when it jumps back down, crashes back towards the nucleus, it gives off that light. So it absorbs and then emits. When it absorbs, it takes in certain colors. So why is this color missing? Because the electron got it. Why is this color missing? Because the electron has it. So these are the black lines, or the absorption spectrum that we see when the electrons jump up, and then they hang on to it, nobody else gets to see those colors, and then eventually it goes back down. And when it goes back down, it gives off those colors. And now we don't see anything but those colors. And that's what we call an emission spectrum, or a bright line spectrum. Nice colors. And that helps us identify elements. All right, so now let's talk about electrons, not just jumping back and forth between energy levels, but completely jumping out of the atom and going somewhere else, or completely jumping into the atom, to the electron cloud. So, all group 1 elements. This is where your understanding of the periodic table and electron configuration should come into play. All right, so that should move. Now, if I'm looking at group 1 elements, which are these guys, hydrogen, lithium, sodium, and so forth, they all have one valence electron. They want to get rid of that one valence electron. So they're going to lose it, and when they lose it, they're going to become a +1 charge. So if we looked at, sodium. If we look at sodium, we know it's going to end in S1. And in fact, it's going to be 1, 2, 3 S1. So here's that one valence electron. What does it want to do? Kick it out. So sodium normally has, let me erase this here. Sodium normally has 11 protons, as we see atomic number 11, and it's got 11 electrons normally. But we just decided it's not happy that way. It wants to kick that electron out. So it's going to go from having 11 protons and 11 electrons to 11 protons and only 10 electrons. What does it have more of? More protons. How many more? One more. 10 versus 11. So it's more positives. We put the plus there. How many more? One more. So it makes +1 ion. Now, if you have 6 valence electrons, what are you going to do? Well, if you have 6, that means you're over here, and you're 2 steps away from the noble gas. So if you have 6, you want to get 1, 2. You want to gain 2. Now, oxygen was one of those guys. Oxygen has, as an atom, 8 protons and 8 electrons. Now, 6 of those are valence electrons. So we know that the valence electrons are not 8, it's only 6, and we want to gain 2 more. So the 6 is going to go up to 8 by changing the total number of electrons. So oxygen is going to have 2 and then 6 valence electrons. It's got 2 in the first energy level, then 6. That gave it the original 8. But it wasn't 8 out here. It has to be 8 out here. So it's going to gain 2 more electrons, making that an 8. So now it's got 2 plus 8 equals 10 electrons. So the grand total is going to be 10. When it does that, it has 2 more negatives, so oxygen makes a -2 charge. And so does everybody else in group 6. Now, nitrogen and phosphorus. These guys are in group 5. So they have 5 of their own. So let's talk about nitrogen. Here's nitrogen's situation. Nitrogen wants to gain 3 more. 1 right there, right there, right there. So nitrogen's going to gain 3. So will phosphorus. Because nitrogen and phosphorus, oops, erase that and pull this out. Nitrogen and phosphorus are directly above and below each other. They're in the same group. They're in group 5, so they do the same thing. They have the same properties. If you have 3 valence electrons, if you are like boron or aluminum or gallium here, you're going to give away 3. You can get 1, 2, or 3, or you can give away 1, 2, or 3. If you have 3 electrons, here's aluminum, you've got 1, 2, 3. No one's going to give you 5 to get your octet. Instead, you're going to kick out 3, and you make aluminum +3. And finally, if you end in this, you don't care about your D's. You only care about the 5th energy level because it's the biggest. 2 plus 5 equals 7. You're going to end up gaining 1 electron. So that'll give you from 7 up to 8. You have your octet. You're nice and happy as long as you gain 1 electron. All right, cations, you should be thinking the little t in the middle, little t in the middle of the word metal, and the t makes you think positive. So these guys have more positives than negatives. How did they get that way? Well, they lost some electrons. Anions are negative nonmetals. These are your nonmetals. They're on the right side of the zigzag line. So these are your nonmetals. And they're negatively charged. How do they get negative? Well, they gain more negatives. So if you start with, I don't know, let's pretend we're fluorine. If you start with fluorine, you have 9 protons and 9 electrons. Fluorine is in group 7. It's not happy that way. It wants to get 1 electron. So 9 is going to become 10, and it's nice and happy. It gained 1 electron, so it's a negative 1 charge. Oops, fluorine. All right, now I've been drawing electron dots for you right along here, but you should be able to draw these yourself now. If you look at sodium, sodium is in group 1. You've got to first know what group it's in, what's its situation. We'll leave this here. So here's sodium. Sodium's in group 1, so that means it's got 1 valence electron. Here's sulfur, right there, in group 6. So it's got 6. So put 1, 2, 3, 4, 5, 6. Doesn't really matter where you put the dots as long as there are 6 of them here. Here's chlorine, right there, group 7. Draw 7 dots. It's 1 away, needs 1 more electron right there. And here's neon, boom, right there. Yeah, it's got 10 total electrons, but we only care about the outermost 8. So you can draw 8. So whatever the group number is, that's how many dots you draw. So group number equals valence electrons, which equals the dots you draw whenever you draw a Lewis dot or electron dot structure. The only exception is helium. Helium only has 2. 1, 2. That's it. It's nice and happy. Doesn't want to play with anybody else on the periodic table because it's happy with its situation.